So today's class is going to be recorded. There's going to be snow soon outside of my office, and I'm going to get it done and then just head back. Okay, so start. Mm. So yeah, let me firstly share the screen for the iPad. Okay, so currently, let me see. Currently, we are gonna firstly talk about basically finish up this part of decision trees. So it's gonna be something we are just um, we didn't actually cover within Unit 1. However, this is still Unit 1 material, but it's gonna be not a huge emphasis for the last homework. So the last homework is being designed, and there will be more theoretical questions rather than implementations. But we'll see. So currently, yeah, let's quickly go back to the idea. So basically, we're setting up a tree. Okay, so when we talk about the ID3 algorithm, so this is a little bit different. So ID3 algorithm handles the discrete feature targets. And now, if we have more targets, then there's a possibility that that there are too many different output the possibilities of targets, so that the most informative feature uh, is something you probably you do not want to capture. Okay, so for the example here is that okay, if you want to learn things about the financial information of a lot of customers, so you don't really want to get these kind of credit card information that is specific to every individual. So that's something that's definitely very informative, right? But it's not really important as a feature as to what you try to learn. So here the idea is that okay, so for these entropies, so these are the from the first part of the decision tree notebook. In case you don't know, so please, if not, if you're not familiar, please go back to look at that. So. So the conditional entropy, the information gain, these are already known. Okay, but now, so basically, once again, we for ID3, we look for the feature that gives us the largest possible information gain, so that uh, so we can set up a tree using the features with higher information gain to be on the upper part of the tree. Okay, so starting from the root all the way down. But now what's different here is that okay, for each feature we also calculate the entropy of the feature. Okay, so the larger the entropy of the feature, this feature itself has too many different possible values for the feature. If that's the case, then we penalize this kind of feature by dividing this entropy there. Okay, so now we want to see if this improvement in terms of the computation. So we're gonna soon look at that in one of the examples. So yeah, right. So this part is the example we're gonna look at. So so later I'm gonna update the yeah, well, I actually updated that notebook in the course website. So, excuse me, in the GitHub repository. But I'm gonna show you guys soon about the data. So, all right. So we covered these. Yeah, right. So the comparison. Okay, so let me quickly get you the comparison of the algorithms. Okay, so earlier we have ID3. Basically, we look for the most informative. we look for the most important features. So let's quickly look at the data. So basically, we have a bunch of customers. Let's say 14. Okay, and now we have income within different ranges. We have debt information, high debt, low debt. We have credit history being the unknown or bad or good, and we have finally the risk. Okay, so whether the customer is high risk or low risk or moderate. So the risk is the last feature in the table in the data table that we want to learn, because basically we want to learn what customer is high risk, what customer is low risk, what customers are in the middle. Okay, so for high risk, you certainly as a banker, you probably do not want to loan money to that high risk customer, and so on and so forth. So okay. So that's so essentially, if you are doing ID3, essentially you're just looking at you're just gonna select the features one by one by looking at the information gain out of the remainder data table. Okay, so that's something you already know. But now here, the algorithm we have established is yeah, it's different. Okay, the algorithm is different. So let me try and see if I share from this side what would be. So replace current share. Okay, so I'm gonna entire screen. I'm gonna share entire screen. Right. Um, Minimize. Okay. Right. So that. Okay. So here. So this which okay, this is the decision tree part. All right, so yeah, so this is the tree that we're looking at right here. So this is the one that we modify. Okay, so this is from my decision tree one notebook. So what you're looking at is the same data set. Okay, so just to so the 14 customers we have. So yeah, well, the display looks a little bit weird for the tables because once again, yeah, let me get this to the left hand side. So these type setting is a little bit different because in the table you have the dollar symbol on the left of 15K to dollar symbol 35K. So now between the two dollar symbols, the markdown is viewing it as kind of a LaTeX format. So which is a bit weird. So you see here over dollar symbol of 35K. This is reasonable display, but these ones are a little bit messed up. But the data is going to be the same. Okay, so now here we the screen is a bit narrow. Basically, the root. Yeah, well. So let's just look at this. So basically here, the income now for the old ID3 algorithm, the income is going to be the most informative feature. So that we have the lowest income, the moderate income, the high income, and then that's the first root. Okay, the root node, and then here this is for the lowest income, this is high risk, it's pure. And then for the other two nodes, we have the feature to be a credit history. Okay, and then for credit history branch into bad, good, and unknown. And then for the unknown, finally we have the third level of a node to be the debt. Okay, high debt is associated with high risk, and low depth here is moderate. So it doesn't look to be a very reasonable uh, thing, in the sense that here because it's kind of like lack of information for credit history. Okay, so All right, but basically here, this other node here is basically saying, okay, uh, we only need to the second layer for classifying all these different risk levels. So that's the old ID3 algorithm. That's from the first part of the decision tree. Okay, so make sure to go back to this decision tree to look at decision tree part one to look at the ID3 algorithm. Okay, so in the homework, I'm going to try to design things about computing these information gain and entropies. So that's that part. Okay, now what about the new algorithm? This C4.5. So here we penalize. Okay, so for those features with a lot of different values, we divide by the entropy of that feature. So here it's indeed a different tree. Okay, so still the highest is income. So even after division, is still the best one to choose. But then now you can look at the branch here. It's different. So here this is credit history. Okay, for this the ID3 algorithm for the middle for the second layer. But now here for this moderate income, we have now the debt. Okay, to do the separation. Okay, instead of credit history directly. So now debt is the second layer. Now the low debt will be moderate, and high debt we finally look at the credit history. So bad, good, and unknown is going to be high. Okay, so you can see here. So so now for the person for the customers with the highest income range, now the credit history part is roughly the similar thing from before. So now you do see the distinction. Okay, so credit history unknown, debt low is moderate. Uh, so that's basically kind of like the same way that you summarize the data, but here and now the decision tree is not really looking at the credit history. So the difference must be that the credit history here, you see, it's always three different values of the feature. However, this one in ID3, this feature here is sort of uh, informative. Okay. However, if we do the division now within this sub branch, okay, within the sub branch, it looks like depth is not that informative, but once you divide by the entropy of the feature, then depth is better. So that's the idea here. Okay, so that's indeed a very big distinction. Okay, so and then we're going to look at the cart algorithm, so classification and regression tree. So now this is the algorithm that now handles continuous target. Basically, the target value can be a continuous variable. So you could have two decimals numbers and a lot of them. Okay, so let's go back to excuse me. Let's wait. I want to share the screen. Share screen. Start. And this will stop the other one. Okay. So let's continue. All right. Okay. So yeah, cart. So now what's different? What's different with cart? So in case you need to catch up. So for entropy, okay, so entropy here is going to be it's going to be calculated by pi times the logarithm of pi, okay, base 2. But once again, since the logarithm is relatively speaking expensive comparing to the linearized version of the computation. So here, the Gini impurity here is even more efficient. Okay, it's much cheaper in terms of the computations because once again, what's the difference? The difference here is that um, when the data is large, the issue for C 4.5 is that when the data is large, the logarithm calculation is too many. Okay, so this is sort of like a linearized computation, but still the Gini impurity is efficient to compute, and also it penalizes. So it gives a large value uh, if you are impure. Okay, if you're pure, once again, the sum of PIs, right? For each PI is going to be the population of that particular class. Uh, in terms of ratio, of course, the sum of PI is always going to be one. So now, if the PIs are roughly similar values, like a uniform distribution, let's say 1 over k. So this thing is going to be 1 minus k times 1 over k squared. Okay, so the summation right here is going to be k over k squared, which is 1 over k, which is small. So 1 minus that is going to be really close to 1. Okay, the difference is k minus 1 over k, right? So, but now if it's pure, then what do you know? You know that one of the PIs is going to be 1, the rest of them are going to be 0. So the sum of squares is also going to be 1. So the difference is going to be a 0. Okay, so this tells you, okay, if I'm pure, then the Gini value is going to be 0. But if not pure, then the Gini value is going to be close to 1. Okay, so this is indeed sort of like penalizing. Okay, so I want to get the Gini values small. Okay, so that's really likely. That's really like the entropy that we have for each data set. Okay, so the the entropy here is a little bit more complicated because we have logarithm, right? All right. So basically, the algorithm is gonna based on the Gini impurity. So and the idea here is that okay, we want to do a splitting of the data. Okay, so we're not gonna branch upon different values of the target anymore. Okay, we're gonna split. Okay, it's gonna be a sort of like a threshold we need to look for. Okay, so let's suppose it's a threshold A, then you have a set S1, that's all the data that's having X within my threshold A. So you can say this is X less than A, or this is like X larger than A. But of course, here your your feature could be multiple, okay? Or uh, well, finally, if you have a bunch of different criterions, then essentially you have intervals or uh, 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 like yeah, well, it's basically intervals. So here we're writing set notation. Okay. So now you see for each threshold, okay, once that's given, I'm going to calculate the Gini in terms of the two sets. Okay, so this is once again, this is sort of like the population. This is again the population, which is 1 minus p1. And so we have the separation that we have S1 and S2, and now for each uh, S set, we're going to look at the the Gini impurity quantity here that's calculated from above. Okay, so still that. All right. For each feature, okay, for each feature, you're going to have a population, and then you will be able to calculate the Gini S1 or S2 value, and then sum. Okay. Once you summarize, you will be able to have a Gini value for each feature, and then you select the feature based on that. Okay. Yeah, indeed, you want to look for the optimal feature and threshold such that the whole thing is minimized. Okay, so this is the key there. All right. Here let's look at one example to see what's going on. So this simple example is basically saying, all right. So summarize. Yeah, quickly summarize. Iterate through the sorted feature. So of course you want to sort the features. Okay. So sort the feature values. Sort feature values. Mm, so you need to sort all the feature values. And then for all the feature values, essentially you will need to think about all the threshold possible. Okay, and now on the left hand side and right hand side, keep track of the samples. Okay, on the left hand side and the right hand side. So here let's think about this feature value to be one dimensional. Okay, so it's uh, an axis. Okay, I'm gonna have a bunch of data points. So there could be many values. But then all the data, okay, so you have okay all the things sorted, and then every value cut in between the two values is going to be a possible threshold. It's going to be possibly a lot. And so which is why we want to iterate through all such things. Okay, and then let's say once you find a threshold like this. Okay, so this is separation. Okay, on the left I have 1 point, on the right I have the rest of the points are five. Okay, so that's so here the second step is basically keeping track of the numbers so that you actually know what these are. All right, so S1 and S2, you know what they are, and then for each set you're gonna calculate the Gini. Okay, for all the features that you want to calculate. Okay, so and here increment or decrement by one after each threshold. So from them we can calculate Gini in constant time. All right, so the now look at the example here. So we have what we have x values, we have y values. So x we have a bunch of x values, so 1.5 all the way down to 2.9. We're sorting. And then for y values, we have actually the label. So this is sort of saying we have the x points and we sorted them. Yeah, well, it's not sorted yet. Okay, so but here we of course want to sort the x values, and then we want to classify. Okay, so we want to sort of give a design a tree. Okay, to associate the x values to data, right? So yeah, we have five data points. So let's say we have these as x1, x2, x3, x4, x5. So yeah, let me erase 1 point. Okay, so we have 5 points. And then once again, we have eventually six thresholds. Okay, so if you use this threshold, you're basically saying everything is on the right hand side. They're in the same class. And if you're using this one as a threshold, then you're basically saying the 3 points on the left are one class, the 3 points on the right are one class. Okay, but basically one threshold will give you a split of a node into two different branches. Okay, so that's the idea right here. Okay, so now here the algorithm says, well, we want to keep track of the yeah we want to go through all the possible thresholds. Okay, so essentially what does it mean? It means okay, I have the left and right. Okay, so and now the all the possible thresholds are six of those. Okay, so it's gonna be let's say we start with this one. Okay, so then we have x1 all the way down through x5 on the left, and then there's nothing on the right. Okay, so that's one class. That's one situation. Here I'm gonna calculate the Gini for S and now A1. Okay, so mm, so A1 is my threshold circled there above. Okay, so and then now I'm gonna move. Okay, so this is gonna be x1. It should be x1 all the way down to x4. And then the right hand side is going to be x5. And then this is going to give me another Gini value, right? And this is continued, okay? So this, we just do one by one, and eventually we'll end up with the one on the left hand side. So so yeah, let me keep that. So this is going to be empty set. Mm. So yeah, it's kind of unnecessary jump. So this goes down, this goes down. So until the last one is x1 through x4, x5. So this is another. But of course, there could be some repetitions, okay? Because eventually on the left, on the right, these two cases are roughly speaking the same thing, okay? But the things in the middle are probably not that. So here we have what? We have A6. Okay? And of course, here essentially you are trying to compute the smallest, okay, the minimum, okay. You're looking for the smallest possible. So the thing you want the thing to be minimized, right? So and let's see. So now how do you calculate the Gini? So here, let me quickly mention that so this thing is modified from entropy. So that's decision tree one, okay? So that's what we have seen from before. So everything is pretty much the same. So here we have a best Gini. So that actually it may if it confuses you, then you can delete this part, delete this part. So basically, this gives you the Gini value. Okay. So there isn't really a lot to say here. So basically, you're looking for all the target values. Okay. So each different target value gives you a class. Okay. So these are unique classes. And then M is the number of different classes. Okay. And now, so, and now M is that, so this N of M is actually that PI there, right? So this is like the population distribution here. So essentially you just have PI squared and summed over all N. Okay. So n parent is actually the number of data within the data set that has the same target value C, right? So for all the class, for all the class, you are separating um, the number of data there. So this is Boolean, right? And here for every class for every uh, data within class C, you're gonna sum, and then that's gonna be just counting, okay, sort of counting, and then essentially that n over there is just the counting, just the population you're dividing, and so you get a PI. So there's nothing really special here, okay. So this is modified from the entropy function there. So Yeah, well, of course. Yeah, so let's just continue here. So the Gini value can be calculated in a straightforward way. All right. So it probably is not necessary to go back to look at the calculation, but here, let's see. Okay, now we look for the best split. This is a relatively speaking important part. Okay, so now this part is we are looking for the best split. So that's actually the way that you sort of determine the root node and then go down branching. Okay, so this is the way that you decide how to branch. So the best meaning that the average impurity of two children is the smallest as possible. Okay. So you are branching and you are also looking for the feature. Okay. So just now we have only accessed the only one feature, and then you don't really have a lot to do. But then let's suppose you have a table and a bunch of features. Then essentially here you are branching and you also you have the thresholds and you also have the features you need to decide. Okay, so that's important here. Okay, so so there isn't really a lot to say for the top part. Okay, so getting the features, getting the features, getting the targets, uh, so a unique target, all target values. Uh, and that's the Gini, right? So here this best Gini is now sort of important because here we are looking for the smallest possible. So you don't really need to update if your Gini at the moment is better, which means larger than the best. Okay, but if it's smaller here, so here if this is smaller, okay, if Gini is smaller than the best, then update. So update if Gini impurity is smaller, sort of like improved. Okay. Um, Comparing to the current best. And then here, the best feature you need to find out and the best threshold. Remember earlier, we didn't really specify. So here, when we talk about these crosses, okay, so they can be considered as midpoints or anything in between these data points, okay. But if you go down, so essentially every time you're sort of like thinking about the set of data points, so you don't really need the thresholds. But now finally, if you want to determine the threshold, here you are just picking the midpoints between the two different thresholds. Okay, so this is one data point. Okay, this is the next data point. But now you just keep the just the average, which is the point in the middle. Okay, so that's something like that. Okay. So you have two data points, and the threshold here is the cross midpoint. All right. So of course, you can see that now the Gini left. Okay, the Gini right, they are just the Gini values for the numbers on the left and numbers on the right. M is what? Yeah, M is the different target values. Okay, so here M is this is number of target values. Target values. So right, and that's calculating the so okay, that's the initial step. So you have the best Gini as one Gini value. Okay, and then these are not captured. Okay, but then we look for all the features. Okay, look through the features. That's a really large for loop. That's all the way below. Let me get another color there. So that's looping through all these. Okay. And the loop here is basically saying, okay, now for everything below, we are just we have all the m values, okay, separations, and then we just do one by one. Okay, so that's that. That's uh yeah, and then for the points on the left, for the points on the right, okay, that's the Gini values. Okay, so the points on the left, the points on the right, these are again the PI values. Okay, there isn't really a lot to say here. So, all right. So now, if you look at the example right here, what it does is okay. The best feature, of course, is x. The best threshold is 2. Okay. So so earlier we have a bunch of data points, but so yeah. Let me quickly give you guys the what tree essentially we are getting here. So for these data, okay, so that's these are this is the line. We have 5 data points, right? So let me quickly just write them down. So we have 1.5, 1.7, 2.3, 2.7, 2.9. And I'm gonna give the labels to be 1, 1, 2, 2, and 3. Okay, okay, so if you want to separate, right, you can say this one is these two are the thresholds, right? But then indeed the first threshold that they compute is a 2. Okay, so 2 is what? 2 is this midpoint. Okay, so it tells you the first the root, okay, is x larger than 2 or less than 2. So that's the root. And then less than the thing is less than the roots. Now we have all the data points to give you 1 as the label, right? And now, okay, for from the right hand side, we need to branch. So then you don't really need a lot of things to do. So now you ask whether x is larger than, so this is gonna be the midpoint, which is now 2.8. Okay, so x larger than 2.8, x has it. So this is yes or no. This is no. So yes, no. And if it's larger than 2.8, this the class is 3, label is 3. If it's no, then it's 2. Right. So that's the tree then. So this is the decision tree that you're looking for. Okay. But sort of how do you decide which excuse me, how you decide which threshold you pick up first, right? So that's based on the Gini values that we calculate. Okay. All right. So now the last one is data. Is the problem we have already seen from before. This is the average data that we have seen for these the data for the flowers. Okay. So all right. So essentially here you still need to get a subtable because essentially once for this algorithm, okay, once you decide a node, then you only look for the data that's remaining. And then basically what I'm saying here is that okay, you start with these 3 data points. Okay, so essentially you remove the a bunch of rows and columns, and then you are concentrating on the rest. Okay, so that's really standard. Okay, that's what we have seen from before. Um, Okay, so that's Iris data set that we mentioned. Uh, so yeah, to get the subtotal, that's same thing from before. Okay, and now build a tree. So so yeah, the thing here is there isn't really much to say, but here we need to do the best split for all the data, okay, to get the best feature and the best threshold. That's the initial step. Okay, so that's the first node. Okay, that's the root node that we need. Okay, so root, which is to associated to what? Associated to lowest uh average gene impurity. Okay, so that's that part. And then so here now that's building up the tree. Okay, we have a lot greater than the best threshold and less than the best threshold. That's the branching. Okay, so this is specifying what left and right are. Okay, so that's the branching part. And then here you see for uh if count left is if the count left is one, the things on the left, we try to see if the things are pure now. Okay, uh so this is saying, okay, if the value on the left here uh mm, oh, concept is this. Concept is whether you have the unique target value. Okay, so this is pure. Okay, so if the concept equals one, if this is pure, then you're done. Otherwise, you split. Okay, it's the keep on looping. So you get the subtree and then just build the tree from here. And this part is also pure on the right for on the right. Okay, this is also keep looping. So get the subtrees. Okay, so get the letter nodes all the way until every node is pure. Right. So here, okay. So this is the yeah, this is the data pretty much. Mm, yeah. So let me quickly share the screen from this side. All right. So Irish data. Okay, I need to get it wider. Uh, okay, that's okay. This is probably the reason. So it's from the Jupyter. So yeah, okay, we'll look at this. So basically, you see the petal length is the root. Okay, so we then look at the petal width greater than or less than two values, and I'll get the third layer, which is the petal length again. And then we split even further as fourth level, which is the petal width. Uh, and then it's the petal spell length. And finally, we have the spell length here, sample length, sample length here. So we we have what? We have one, two, three, four, five levels. Okay, so that's the tree that we established from here. And of course, if you worry about the over parameterization, then there's other steps that we need to do to do pruning. Okay, but for more comprehensive setup, all right, we will once again think about the decision tree. So you are building up a tree based on the data. So we mentioned that the tree built from the data is sort of like a summary of the data that you have. So if you get a tree such that every node is pure, then you sort of summarize it to the end, but it may be over parameterized. So there may be too many levels. But here, what we can say, and earlier we mentioned, okay, you probably can do pruning to remove the certain leaves so that the validation error is the smallest as possible. Okay, but here what we are looking at um, is that the data does not have uh, sepal width. Okay, so if you look at this is a petal with sepal length. Okay, so indeed there are certain features that are not so important here. Okay, so the sample width doesn't really occur within the decision tree that we build up. So that tells you what? That tells you this feature probably is not that important. All right. Okay, so that's all we need to talk about for decision tree. All right, so now let's jump into um, so we have one more class, and then we can talk about neural network. So the neural network is something that's I can say not entirely new. So let me start the sharing here. Oh, I have multiple people sharing. Weird. That may be an issue. So here, okay, so okay. So yeah, so let's just continue with the neural networks. So it's not an entire alien, but let's quickly look at what we need to discuss for neural networks. So we have three parts. Okay, so the first and second parts they are sort of like theoretical, and which is not really complicated. But then the last part is the implementation. You do have to get the things done on using your own programming skills. Okay. So that's mm, okay. That's it was all. So neural network. So what do you actually do? So essentially, let's quickly review what we are looking at right here. So essentially, what do you have? You have n data points xi yi, right? So you have n as the cardinality. And then X are the d-dimensional feature. Okay, it can be like an image, and the Y uh, could be the label associated to the image. Sometimes it's like the mnist digits, like from 0 to 9. Sometimes it's like whether it's a dog or a cat. Okay, so it could be binary. It could be k class. Okay, so it's basically just a possibly integer. Okay. And the goal here is that we want to get a model, okay, f uh, sort of like a vector function with x and theta to be the inputs. Okay, so x is the any feature, okay, combined now with the model parameter theta that you have, and you will be able to calculate a vector between 0 and 1, sort of like sort of like a distribution. So that's the thing that you're looking at here. So model parameter is going to be theta. So now the thing cth component is going to be a component of the vector. So it will be a probability, okay? That's where your xi data is in class C. So if the thing is close to zero, then it's not likely to be in class C. If it's larger, if it's close to one, then it's likely to be in class C. Okay. So when you do the classification, this is essentially saying I'm looking for the argmax among all classes of f sub C, the prediction of the model on the ith data, right? Wait. Mm, Oh, so you would expect your data xi that's going to be predicted to be your uh, class C, okay, class yi. So you would hope that okay, so I'm getting the bracket y. So this is just saying okay, I'm looking for the class okay according to the prediction okay the largest probability value is going to associate to uh, that particular class. But now once that class is found, I wanted to match with the true class. Okay, I want it to match with yi. If not matching, then I'm gonna penalize. Okay. So now, so this is something you have seen from before, which is logistic regression. What do? You actually have a pre-activation vector z that's just wx plus b. Okay, so if you think about the model earlier, we have what we have just a linear model. So that's actually the W matrix combined with a column of ones, and then you multiply by uh oh excuse me uh yeah well that's actually b. Okay, that's sort of like x well. Mm, yeah, earlier you have what? Earlier you have W. So yeah, so earlier you have okay, earlier you have x as rows, okay. So they are the data and the W is the weights, okay. But here it's sort of like the opposite way of thinking. But anyways, earlier we have to augment a column of ones with the data x, okay. But here we are not going to do that anymore. So we separate the bias, okay, with the weight matrix. So W is the weight matrix, B is the bias. Okay, so if you must, you can say this part is from. So W is fixed. Okay, so this is just out of a linear subspace generated from the column space of W, right? But then you sort of like doing a shifting. Okay, so that B part is the bias. So essentially, you're training. You're trying to learn. Theta is going to be the combination of the matrix and the bias, okay, the weight matrix and bias. And essentially the model that you do is that, okay, I have this Z, but then I want to make sure that this thing is close to my Y vector. Okay, so mm, yeah, Y vector here, Yi is going to be labeled as the vector that is one hot of the class Yi. Okay, so this is the standard basis. I have Yi as the class. Okay, so Y is my true label. So if it's let's say if it equals C, okay, so that's basically saying my vector has only one that's the C entry and every zero everywhere else, right? So essentially you want to try to match C you want to try to match Z as vector to W, but here the activation is saying that okay, if I have imbalanced entries of Z, okay, then the exponential function will make the difference more significant, okay. So this softmax is what you have learned from before. So this is trying to make imbalanced vector so that larger exponents will have much larger entries in the vector. So that's softmax we have seen. So and it always gives you a distribution. Okay. So that the components are one. The components sum to one. All right, so now here, so that's the model. Okay, so we have, so for logistic regression with softmax, we have a linear mapping in the middle, but then we compose with a softmax function, so we will get uh, a vector output function. All right. So now, so how do we penalize? So we want to make the a functional objective function, and then we minimize the objective function, right? So here, what we are doing is we use the cross entropy loss. So what do you want? Essentially, you want this thing to this f xi given theta, this vector, okay, you want it to be close to the vector yi, which is defined as e's little yi. So the bold yi is the one hot, okay, one hot vector. So one hot vector of the label. So you want these two vectors to be close. Okay, so you're basically saying, okay, for the ith data, this distribution needs to be close to the one hot vector for that class. Okay, so the closer the better. So essentially, when you're doing this, essentially you're just sort of doing the cross entropy, so that you are essentially you're looking at the here. This is the uh, yi component. Okay. Why is that? So here, essentially, you do not really care about the rest of the components. So remember, this cross entropy is written as the negative of the each qi, okay, times log pi. So that's something you have done in homework. Okay, so your q. So your Qi sum to one, your Pi sum to one. So when P as a distribution matches Q, then this cross entropy is minimized. Okay, so of course you would want this thing to match. So you want to minimize the cross entropy. But now remember, this y vector is what? This y vector is one hot. So you only have one of the y values to be one. So that's exactly where that so that's exactly where my little yi equals one. So that's exactly my ith component. Okay, so yi component right here. So that tells you, okay, although you have a softmax as an output, but then essentially you're just looking at that particular component. Okay, so what that are yi's place. Okay, all right. So this gives you a loss function. Okay, so essentially for each individual data I with index I, okay, from one all the way down to cap n, you will have a loss function. Essentially, you have you're summing over all these losses. Okay, so minimize uh this is empirical loss. Okay, so summing over all the losses. Right? And of course, if you want to avoid overfitting, this is a regression that you can do. So this is actually what this is the ridge regression. Right. So and of course later you're gonna uh so what you eventually do is that okay, I try to minimize and I can do SGD. Okay, so that's what you have seen from before. That's just logistic regression. Okay. There isn't really a lot to say, but here now, if you look at the diagram, this is what we have established earlier. So whatever, so this is a handwritten digits as a figure. So what you do is flatten so that I have a vector uh, uh, for my data. Okay, and then here I'm now. So now here for each, so right, y is 10 dimensional because now y is one hot. Okay. So here, this is exactly why I have 10 by 784. That's my D, that's my K. Okay, so 10 classes, right? And then the weights is going to be W, which is a large matrix. And this is the pre-activation, right? And basically every component wait yeah every comp this is my Z1 all the way down through well, excuse me and Z10. Okay, so or you can say this is Z0 to Z9. That's totally fine. But basically these are the components, and then you feed to softmax, which is making a distinction between the exponents. So the smaller exponents will give me uh, even smaller exponential values. Okay, this is normalizing. You have a probability. So remember when we do binary, then this is a sigmoid. Sigmoid is really nice in the sense that this is differentiable, and also softmax for a multi-class learning. This is also logistic regression. This is also differentiable. Okay, so this is a really simple case of uh, what we're going to look at is neural network. So this is already a network, right? But now for neural network, this is a little bit a more complicated structure. And so let's see, we have two-layer neural network. So what do we have? We have the inputs, we have the hidden layer, okay, and we have the output layer. All right, so now in this example, what do we see? We have the input layer, we have x1 to x5. So now this d equals to 5, okay, in this particular figure, okay. And now the gray ones are the hidden neurons. So we have one hidden layer uh, and one upper layer. So here we have four nodes, right? So this H value is 4. So basically, we have a vector. Now we get to the middle Z vector as the middle layer. So what you know is that you have these are W1 and D1. These are the parameters, okay, for that layer. So you have W1 X plus B1. That's my Z as the pre-activation again. And then G is my activation, okay? Uh, G is element-wise activation function, possibly nonlinear. Of course, you must be nonlinear because the mapping that you have done, that's linear. Okay, if G is linear, then everything is linear. Then that doesn't make sense. So that's my pre-activation. And once you compute this value, that's going to be my that's going to be my A. Okay, so this is my that's my Z. Let me write it here. So Z, you will get into the Z nodes, and then once you get, you will get A vector back out. Okay, so that's my A right there. And now A is going to be fed into W2 and D2. So you will have W2 and A times B2. That's the pre-activation for the second layer, because that's from here. And finally, if you feed that into softmax, that will give you uh, this kind of a composition, and that will give me the final output here. Okay, so softmax is oh, wait, softmax. That's the activation for the output. Mm, right. So now for the entire model, what do we have? We have uh we have the predetermined dimensions. We have 5 dimensions, 4 dimensions, and 3 dimensions. So 3 dimensions. So the right hand side the three and the left hand side the five, they are determined because of the dimensions of your input and output. But here that can be determined by the design. Okay. But once that's decided, then the dimensions of W1, W2, and D1 and D2, they are all determined. Okay, so so you can say this H is a hyperparameter, but of course, the larger, then you will cover the smaller ones. Okay, so the special cases. Okay, so the hyperparameter. So, but once that's decided, then the model parameters are just the W and B vectors. Okay. So, then now everything is specified. We still, since we are looking at the softmax uh, as the final activation. So softmax. Let me put it down. So because softmax is used as the activation, so the loss is still going to be cross entropy. Okay, so it's going to be like this. So still, this is the yi component of f, okay, of the model. So yeah, let me erase that bold symbol here. It's not really necessary. Okay? But of course, if you want to change the uh, objective function, that's totally fine. Okay, so now what happens if you want to change to a sigmoid? So if you want to use a sigmoid and a logistic loss, okay, so that's basically saying the g function um, and the final layer, they are both sigmoid. Okay, so you then essentially what do you do? You just realize, so there's a sort of like a problem. Okay, so the problem here is that, okay, so if it's component wise, then it's possible that, okay, this vector, you have multiple components that are close to one. Then then the problem here is that for that particular data point, you you let's say the first and second components are close to one. It tells you, oh, they are going to be classified as both class one and class two. Okay, but that doesn't make sense. So here you do want to penalize the values that are uh, uh, equal to one where the true label is not. Okay, so you want to penalize. So this is penalizing uh so this is pushing the f value to fyi push to one. Okay, so this is trying to make sure that my for the for the yi class the prediction value is close to one. Okay, here this is doing the different thing. This is saying okay for those components that are not yi. Okay, so they in the one hot vector they are zeros. Okay, so now I also want my fj to be close to zero. Okay, so eventually log of one minus fj is gonna be close to log one, which is one, which is zero. Okay, so still everything is gonna be not negative. Okay, so of course the whole thing is not negative. So you want it to get it to close to zero as possible. Okay. So now you do realize this is a sum of k functions. Okay, so essentially you can write it as the k sum. Okay, having yj log fj times 1 minus yj times 1 minus fj. So this is something you have seen from before. Okay, so this is sort of the log form of the loss. Okay, so log form of loss. So in logistic regression, lecture 7, well, in, in one of so one of the logistic regression notes. So in that note, we also have different ways to define the loss function. So here, this is another way. Okay. So if you get the quadratic loss, you can do it like this. Okay. So this is what this is matching the f vector with the one hot vector of y. Okay. The bold one. So if you do that, then this is not using the log anymore. Okay, but you're still trying to get f vector as close to y vector here, right? So of course, then essentially once you design the model, then you do have different ways that you choose the loss function. Okay. All right. So now, when we talk about whether a layer is dense or not, what does it mean? So essentially, if you look at the edges, okay, so yeah, if you look at uh, this right here, so essentially for a node, okay, for a neuron, let's say for a neuron here, so essentially you have what you have the input, let's say vector A, and now every edge is going to be a weight, so it's going to be so this is my zi, right? Let's say this is zj. Okay. So essentially zj is computed from what? It's computed from a1 w1 all the way down to a d wd plus b. Okay, so that's the bias bj. So usually it's j's component of a vector. Okay, so this is what this is w1 through wd as a row multiplying by a plus bj. Okay, so essentially you have j different such rows. Okay, So the entire matrix actually what that W so that's my W. Okay, so let me write the row in the indices also. So that's gonna be my WJ1 all the way down to WJD. That's my WJ1, WJD. Okay, so that's the jth row of W right here. Okay, so if you have, let's say, Wj k to be zero, that means what? That means your AK here multiplying by WJK, which is gonna give you zero times that. So AK doesn't do anything anymore. Okay, so it tells you AK XK in the equation, in this equation. Okay, XK does not affect ZJ at all. Okay, so it tells you one of the edges do not do anything. Okay, so if your matrix W here is dense, then that tells you the entire network is dense. If there are certain ways that zero, that tells you certain edges are zero. Okay, so there are certain edges, let's say pointing from here to here is actually not really activate. Okay, so not actually working. Okay, so that's about the term density within the network. So um, so you do see that okay, every layer you have a linear mapping, but the most important thing here to introduce non-linearity is the activation. Okay, for each layer, uh, there's going to be an activation that's very important. Okay, so now besides the softmax, okay, you have something like this. You are able to choose the sigmoid, hyperbolic tangent, and ReLU. So now ReLU is the function like right here. Okay, so that's the so every activation is a blue function. So it will give from 0 to 1 is from -1 to 1. This is from 0 to 1. But now notice the gradient is 1 on the right hand side. Okay. So that tells you if you want to go negative gradient direction to minimize, you are just pushing to the negative part. So indeed, everything works. Okay. So ReLU is nice because it's constant derivative everywhere except at zero. Okay. So at zero, it's not differentiable. But basically, all these activation functions they can work nicely. So just realize that okay, this hyperbolic tangent occurs in the derivative as one minus hyperbolic tangent squared. Okay, so this for the sigmoid function you have this. Then we calculated in the homework that the derivative of the sigmoid is also easy to compute. Okay, it's a sigmoid times one minus sigmoid. So and then in the next part of the notes, we need to talk about backpropagation a little. But that's also something you possibly have seen in 500. So let's just continue. So now, as for the concept, what do we mean by saying it's deep neural net? So when we talk about deep neural network, so basically it can have multiple hidden layers. Okay, so we have the input layer again. That's my X. So the output layer is my what is my uh so yeah, this is so I'm thinking about notation. So let me see. So here we have binary output, right? So this is going to be my k dimensional and k here equal to 2. So in terms of notation, what do we use? So let's just not do anything for the notation. So what do we actually do? We have the input layer. We have W1 as the matrix and the bias, and then you feed X B1, that will give you what? That give you Z1 as the pre-activation vector, and then you feed to the activation that will give you, let's say, A1 uh, as the output for the first hidden layer, and then you play with W2, B2, okay, which gives you the uh, pre-activation vector, and then you go to activation, then it will give you A2, and finally you have what you have W3. Oh, not even there yet. So that's W3 B3, and then you have Z3 pre-activation and post-activation A3, and finally you have a smaller layer, smaller uh, network that's B W4 B4. Okay. Finally, that's my pre-activation Z4, and then I need to activate. Okay, that's gonna be A4, right? So now, okay, so we have three hidden layers. Okay, it tells you all we overall have 3 plus 2. That's 5 layers. And we have the intermediate parameters, okay? That's W1, B1, all the way to W4, B4. And then what else? So that's the deepness, okay? So you have a depth going from the left to the right, and then we have a width, okay? So here you see every layer, they have what, 7 nodes, okay? So let me stop that. So that's a maximum number of nodes within one layer is going to be called the width. All right. Okay, so here we have X in so we have 6 nodes at the beginning. Okay, so that's certainly not the number of pixels within the figure. So you get the point. So the number of intermediate points within the network. So the maximum number here is going to be the width. Right? So why does the deep neural network work? So essentially, what do you want? You try to uh, learn some decision function. Okay, so this underlying decision function f hat you want to somehow estimate. Okay, so this function f hat is possibly not very nice, uh, but essentially that f hat is nice in the sense that you give me a figure of hat, uh, eventually I will give a 1, and give me a figure of a dog, I'm gonna get a 0. Okay, so to classify a cat. Okay, so that's also always sort of like a perfect function. Okay, so give me a figure, I'm gonna produce you. Give me a figure of a certain dimension. Okay, d-dimensional. I'm gonna classify the correct label. So that's essentially a function. But now you want to approximate such a function. Okay, so a deep neural network can approximate any such f hat uh, up to any given precision. Okay, with arbitrary precision, as long as your depth is sufficiently large. Okay, so this is called the universal approximation theorem. So basically, it says, okay, for any f hat, and any position epsilon, you can always find a Ranu network with Ranu activation function uh, with width at most d plus 4. Okay, so that d is the dimension of the problem. Okay, so no matter what f hat is, as long as your width is at most cap d plus 4, you can specify a depth. Okay, so you can specify a depth to make this prediction. Okay, make this approximation. So so this actually is a nice theorem. That's kind of like a constructional proof. Okay, so so you don't really need a super large width. The depths may really rely on certain properties of the function, but essentially, if you look at the accuracy, this is integrating over the entire RD space. Okay, so now the integral of the residual here is less than epsilon. Okay, so that tells you it can be super accurate. Okay, so but here of course the parameter hidden is actually this. Okay, so the depth could be large. Um, But of course, since this kind of f hat function, okay, so for this kind of prediction text, it's always a complicated function, okay. So essentially, training is not easy because the loss in general is non-convex. Okay, so f hat is not guaranteed to be convex even. And then if you think about the objective function that you set up, so f hat is non-convex, and you have what? You have this kind of uh, quadratic loss as a composition. Okay, so you have an outer uh, function norm squared in terms of the composition. And within the inside, you have that uh, sort of like a perfect function yi, which is f hat. Okay, so you try to build a f bar or f arrow to approximate f hat. So it's always doable, but the optimization problem is non-convex. Okay, so that's unfortunate. So usually what you do is you do SGD and try to look for a local minimum. Okay, so SGD uh, local minimum. So yeah, so yeah, well, back propagation is something we will quickly cover next time, and also we're gonna talk about the implementation of deep neural nets. Okay, but I think the last homework will be not so long. Okay, so it will give you questions in terms of deep neural nets, but also some questions on naive bias and uh, decision trees. Okay, so let me stop the class for now, and uh, I'll see you guys on Thursday.